होगा सर, यहाँ से होता है। क्या था वो? Yes, Dr. Satyabrata.
Good afternoon, sir.
Good afternoon. Good afternoon. Hello, how are you?
Fine, sir.
Yeah, that's a
Sir, how is this
platform
program
to.
going on?
That's a platform to interact with each other.
Yes, sir.
Okay. So in DTU, who is the vice chancellor right now? Hello?
Yes, sir.
Who is the vice chancellor right now in DTU? You are in DTU, na?
Sir, I don't know about this because on 7th, his farewell is organized. Will organize actually. So after that, who will be the vice chancellor? It is not decided yet actually.
Okay, okay, okay.
Maybe
Someone has.
someone from the DTU who will be as acting vice chancellor, and then
Okay.
I think permanent vice chancellor will come.
Okay. So you can share your PPT, whatever, and
Yes,
check
yes,
it.
sure, sure.
Check it here.
Is it
Yeah,
visible?
it's okay.
Okay, fine.
Okay, fine. Just a moment, I'm coming. Huh?
Okay.
So participants are joining slowly and gradually after the second session.
Okay.
So I think we should start.
Yes, we can start now.
So very good afternoon to Dr. Satyabrata Adhikari ji, and welcome to this FDP program on quantum computing at Adhikari IIIT Gwalior. So I'm giving just a brief biodata of Dr. Satyabrata. He did his BSc in mathematics from Calcutta University, Kolkata, and masters in applied mathematics from Calcutta University. Then PhD on quantum cloning and quantum deletion, quantum information theory. That is from Bengal Engineering Science University, Shivpur. And he did his postdoctoral fellow at S.N. Bose National Center for Basic Sciences, Kolkata. Thereafter, postdoctoral fellow at Korea Advanced Institute of Science and Technology, South Korea. Postdoctoral fellow at Institute of Physics, Bhubaneswar. And assistant professor at IIT Jodhpur during 2012 to 2014. Right now, he is assistant professor in Delhi Technical University and doing a lot of research in quantum related phenomena. And he has also been awarded K.K. Mukherjee Memorial Award for the first class in BSc, Dr. Shyamalal Hazara Memorial Award for the first class in BSc, and reviewer of different kind of journals, international journals there. So basically, his field of research is quantum information theory, and a lot of research papers have been published. His credit, more than 47 research papers in different national international journals. So I welcome you, sir, and invite you to start your lecture on teleportation and super dense coding. So you can start, sir.
Thank you, sir. Thank you for the this wonderful introduction, and good afternoon to all of you. So let's start this session now. So I will be talking on this quantum teleportation and super dense coding. So these are the two important application of entanglement. And I think you have already heard about the concept of entanglement in earlier lectures. So I will go through it, but in a brief way. I will not spend much time on the theory of entanglement. So, but for the completeness, I will talk about something about the entanglement, and then I will talk about this quantum teleportation and super dense coding. So in this way, my outline of my talk is in this way. We can plan of my talk in this way, that first of all, I will give you the general introduction. So in this general introduction, I will cover some topics which we need to introduce the subject quantum teleportation and super dense coding. And then I will talk about in detail the teleportation and then super dense coding sequentially. So let us take a quick view on the introduction of this quantum information theory. So let's start from the classical information. So we already know about this, that the unit of classical information is classical bit. And this classical bit can be expressed as these two vectors, K0 and K1. So let me tell you about one thing, that actually I am from mathematics background. So I will give you the flavor of mathematics in quantum information theory. So that's why I have written here that the vector K0 and K1 as a column vector. So the classical bits, this 0 can be represented as 1, 0, and the state 1 can be represented as 0, 1. So if we talk about a quantum bit, so how we can define this quantum bit? So quantum bit is nothing but it is just the superposition of these two classical bits, and we can take this superposition as or expressed in this way: the alpha K0 plus beta K1, where this alpha and beta are generally complex number, and this K0 and K1, which we have already denoted as a classical bit, and this classical bit lies in the domain of the Hilbert space. Okay, so these vectors are in the Hilbert space. So now, if we have this alpha K0 plus beta K1, so in a physical, if you would like to see this qubit in a physical way, so you can just consider it as the state of some photon, and you know that the photon has two possible polarization. One is horizontal polarization and another is vertical polarization. So we can just denote this as our horizontal polarization, and we can denote this as vertical polarization. So this is the combination of horizontal polarization and vertical polarization. So in this way, you can just correspond with the physical observable, sorry, physical system, that is the photon. So now alpha K0 plus beta K1. So since K0 is represented in this way 1 0, and K1 is represented in this way 0 1. So if you substitute this two column vector here, then you can easily get this thing, that is alpha beta. So alpha K0 plus beta K1, this is a vector quantity, and this is a column vector alpha beta. And one condition we must impose on this state, that mod alpha square plus mod beta square equals to 1. So this is the normalization condition. And this mod alpha square gives you the probability of collapsing the state. If you perform some measurement on it, then this state will change. You know that in quantum mechanics, when you perform some measurement, then the state will change. So when you perform measurement on this qubit, then the state will change, and the probability of collapsing the state onto this K0 is mod alpha square, and the probability of collapsing the state onto K1 is mod beta square. So since these are the two probabilities, and these are the exhaustive, only the exhaustive cases, so mod alpha square plus mod beta square equals to 1. So this means that this normalization condition is nothing but it gives you the total probability of collapsing the state either in K0 or in K1. So now, in general, if we define the quantum state, so the quantum state is described by a density operator, rho equals to summation over I pi psi I psi I. So it is the convex combination of all these qubits. Okay, so it is the convex combination of all these qubits, because these pi's are the classical probabilities, and this classical probability summation pi equals to 1, and the pure state you will get. For example, when if you would like to see the experiment, then you can just consider this Stern-Gerlach experiment, and you know that in that experiment, if you have some silver atom, and if that silver atom is passes through some non-uniform magnetic field, then let us suppose this is the non-uniform magnetic field here. So some silver atom is passes through it. So when this silver atom passes through it, due to this non-uniform magnetic field, it is deflecting some stream of silver atom deflected in this direction. Some stream of photons deflect, silver atoms deflected in this direction. Some are in this direction. So if we consider that the probability of probability of deflecting the silver atom in this direction is P1, and the probability corresponding probability in this direction is P2, and P3 is in this direction. So the the silver atoms, when we are talking about the silver atom, so here we are talking about the ensemble of silver atoms. So here not exactly one silver atom is going in this direction, but there are ensemble of silver atom going in this direction. And let us suppose this direction is denoted by psi1, this state psi1. So that means it is a state vector, and this vector going in this direction. So in this way, let us suppose some silver atom going in this direction, and they can be represented in this form psi2, and in this way psi3. So now if we collect this, and let us suppose if we have only 3 directions, then the total silver atom going either in this direction or in this direction or in this direction. So the total quantum state can be represented as the P1 K psi1 bra psi1, P2 plus P2 K psi2 bra psi2, and plus P3 K psi3 plus I3. So it is the outer product of this. So this means that this represent a operator, this represent a matrix. So that is why it is called a density matrix. So in this way, we can describe a quantum state as a convex combination of the pure states. So now in general, if we have n number of ensembles, n number of directions, then we can have n probabilities, p1, p2 dot pn, and corresponding to each and every direction, we can associate this probability. And then if we take the convex combination of these states, then we can say that it represents the general quantum state, and it is described by this density matrix rho. Now this so now since we are encoding the quantum information in qubit, not in classical bit, so quantum information is measured in qubit. Okay. One more thing is that you can see that classical bit can be sent by a classical channel. What do you mean by classical channel? For example, a simple example of classical channel is the telephone. So when you are contacting with your friend, that means if you would like to talk with your friend, then you just call him, and then you can talk with him. Okay, so this is a classical channel. So the classical bit can be sent by this type of classical channel, and you can also have some optics in fiber optics, and through those fiber optics you can send classical bit also. But in the qubit, in case of qubit, we cannot send the qubit just by a classical channel, but we need some quantum channel also. Okay, and we because here you can see that when you are sending some classical bit, so this classical bit may destroy this means I would like to say that when you are sending some qubit with through this classical channel, then this qubit this classical channel may destroy the coherence. What do you mean by coherence? Coherence is this, that means coherence is related with this superposition term. So alpha 0 plus beta 1, this means you are superposition these two classical bits. So when you are taking the superposition of these two classical bits, and when you treat this as a qubit, so and when this qubit you are sending through a classical channel, so it may this classical channel may destroy this coherence, may destroy this superposition factor. So to preserve this coherence factor, so we need some channel that may be described by quantum mechanical quantum theory of quantum mechanics. Okay, so this channel is known as quantum channel. So whenever we will send some qubit from through channel, then we need both channel, classical channel and quantum channel. So now let me talk about some quantum measurement. So quantum measurements are described by a collection of measurement operator. So here the small m denote the number of outcomes, that is mth outcome after performing some measurement through this Hermitian operator capital M. So these operators, when acting on the state space of the system being measured, so then after performing measurement, the state psi, let us suppose the original state is psi. When we perform measurement with this measurement operator it reduces the state. The state reduces to this form. So that means the state will change, and the change at the final state at the output is given in this form. Psi by root over Pm, where root over Pm is the probability. So here root over Pm will come because to normalize this state psi. Okay, so always we have to normalize this state, otherwise we cannot make the total probability equals to 1. So that is why we have to normalize this. So here PM denoting the probability of getting the outcome M. So when you are performing some measurement if you expect that the outcome M will occur, so this outcome M will occur with some probability P. And this is denoted as PM. So that means the probability of getting the outcome M with this probability. So if you do some little mathematics, then you can see that PM can be written as psi dagger psi. Okay, so PM is written, probability can be calculated in this way. So now these operators, these measurement operators, if these are let us suppose if we have sufficient number of quantum measurement operator, and those operators are sufficient to each and every state of the system, then we can say that these operators satisfy the completeness property. So that means this measurement operators are sufficient to measure all the states lying in the Hilbert space. So the measurement operator satisfy the completeness properties if we have this condition, that is summation over m dagger equals to I. So this is the completeness relation, and I think you all have gone through these basic things, because you have already attended lectures, a few earlier lectures also. So if you go through this book, M.N. Nielsen and Ilchon, Quantum Computation and Quantum Information, this is the very first book on this quantum information. So if you go through this book, then you will get all these basic things. Now, let me give you an example of a measurement. So a measurement. So when we have a qubit, and if we would like to perform some measurement on a qubit in the computational basis, so here we can have the qubit can be written in this form: psi equals to alpha ket 0 plus beta ket 1, with the condition that mod alpha square plus mod beta square equals to 1. So this is the qubit, and if you would like to perform measurement on this qubit in the computational basis, so here you can see that we have a Hilbert space H, and we have a qubit system. So this qubit is expanded or spanned by these two basis state ket 0 and ket 1. So these are the basis state in this Hilbert space, and every state lying in this Hilbert space can be spanned by these two basis elements. So this means that the qubit lying each and every state of this Hilbert space can be expressed in this form, that is alpha 0 plus beta 1, where alpha beta are complex number in general, and satisfies this property that mod alpha square plus mod beta square equals to 1. So now since this basis is known as the computational basis. Okay, so now you can see that when you perform measurement, so you can get only two outcomes, either ket 0 or ket 1. So corresponding to these two basis elements, we can construct the two measurement operators, and the measurement operators can be constructed in this way: m0, so it is corresponding to ket 0, and m1 corresponding to m1. So the outcome 0 will this outcome 0 means this ket 0 we will get with this operator m0, and the outcome 1 we will get with this operator m1, m0 and m1. So now this measurement operator must be Hermitian, because it will give you some real eigenvalues. Okay, so that is why measurement operator is Hermitian, so that we can always get the result in a real terms. So now one more thing you can see here, that m0 square equals to m0, this property will be satisfied. So if m0 equals to ket 0 0, so you can easily calculate this. m0 square means you have to multiply this outer product two times. So it will, if you expand this, then you can get the inner product between 0 and 0. So it will give you 1, and you remain with only this first 0 and this last 0. So ket 0 bra 0. So it is nothing but m0. So in this way, we can prove that m0 square equals to m0. And also we can show that m1 square equals to m1 also. So the completeness property relation gives you that m0 dagger m0 plus m1 dagger m1, it is equal to I, because we have defined the complete set of operators. because we have two outcomes, and we corresponding to both the outcomes, we have defined the measurement operator. So that is why it is complete. So M0 dagger M0 plus M1 dagger M1 equals to I. This is the completeness relation. And we know that M0 and M1 are Hermitian operator. So that means M0 dagger equals to M0. So we have M0 plus M1 dagger equals to M1. So M1 equals to I. So this gives you M0 square plus M1 square. This equals to I. And we know that M0 square equals to M0 and M1 square equals to M1. So we have M0 plus M1 equals to I. Just a minute. So after this, let us suppose we have this qubit, which is written in this form: psi equals to a gate 0 plus b gate 1. So now the probability of obtaining measurement outcome 0. So that means when we perform some measurement with the operator M0, then the state collapses to this one, gate 0. So with which probability this state is collapsing to the state gate 0? So to get this, to get the probability, so that means P0 means we will get the outcome 0 with some probability. And according to the definition of the probability, we have this psi of M0 dagger M0 equal gate psi M0 dagger M0 bra psi. So since M0 is a Hermitian operator, so this means that M0 dagger equals to M0. So now M0 square will become M0. So we have psi M0 psi. So you can see that M0 is nothing but M0 operator is this one, gate 0, gate 0. So when you apply this M0 on this psi, so when you apply this M0 on psi, so this means that you will get 0, 0 operator, you are acting on this psi, that is a gate 0 plus b gate 1. So this means that when this 0 taking the inner product between 0 and 0, this gives you 1. And when you take this inner product between 0 and 1, these are orthogonal. So this the inner product will give you 0. So this means that we remain with a gate 0. So M0 gate psi gives you A0. So this part M0 gate psi, this part will become A gate 0. So now this bra psi, so bra psi means you are taking the complex conjugate of this. So it will become A star because A and B are complex number. So A star gate 0 plus B star gate 1. So when you take the inner product between this M0 psi, that is A gate 0, and bra psi, so if you take the inner product between these two, then you will have this thing A star gate 0 plus B star gate 1 bra 1, and you are multiplying with this one A gate 0. So you will get A star, that is mod A square, 0 0 equals to 1, and 1 0 equals to 0. So that means you remain with only mod A square, and in this way this probability is calculated. So the probability of getting outcome 0 will be mod A square. In the same way, we can obtain the probability of obtaining the probability of getting the outcome 1. So P1 will become mod P square. So in this way, when we have already calculated P0 and P1, so the state after measurement, so after measurement, the state will change, and the state will change according to this rule, M0 gate psi by mod A. What is mod A? Mod A is this root over of P0. So root over of P0 gives you mod A. So M0 gate psi, here we have already calculated M0 gate psi equals to A gate 0. So this means that E by mod A gate 0. So that means when you perform some measurement M0 on this state psi, so the state will collapses to the state 0, and the probability of collapsing is mod A square. So in this way, you can perform measurement operator M1, and then the probability of getting the outcome 1 is mod B square, and the state after measurement it will be M1 psi by mod B, and the resulting state will become this one, B by mod B get 1. So that means in this way we can perform measurement on some quantum system. So now after this, we need a no cloning theorem, because all these things, measurement, no cloning theorem, all this we need to explain the teleportation protocol. Okay, so I have to go through this to give you the complete picture of the teleportation protocol. So now, what do you mean by no cloning theorem? So in 1992, Wouters and Zurich proved that an arbitrary quantum state cannot be cloned. An arbitrary quantum state, what does this mean? An arbitrary quantum state means A K0 plus B K1. So whenever A and B are any complex number in the Hilbert space, so this state will become arbitrary. That means we don't know about this state. So when we don't have any idea about this state, so that state is known as arbitrary quantum state. So when we don't have any idea about this coefficient A and B, then this state cannot be cloned. So that is why it is called, this statement stated in this way, that an arbitrary quantum state cannot be cloned. So that means we cannot copy this state. Okay, but later we will see that whenever we have this A equals to 0, so that means whenever we have A equals to 0, so that means the state reduces to this one only, Ket1. So, and whenever you put B equals to 0, so that means this condition gives you the state will become now Ket0. So in these extreme cases, you can see that we got this classical state. So this state is not the superposition of two classical bits, but it is only the classical bit. So whenever we have, we will see in the later slide that whenever we have this type of classical bit, then we can easily clone, and which should be, because we know that we can have some Xerox machine, and in that Xerox machine we can easily copy the classical information. Whatever you are giving in an original, you can just get the copy of that information into some blank sheet. So that means whenever you have constructed this type of Xerox machine, this gives you the this gives you the realization that whenever we have classical information, that classical information can be copied. But if we have encoded some information in this arbitrary quantum mechanical state, then it cannot be cloned. That means you cannot copy it. Okay, so so this thing we can prove it. So if possible, so we can go to the proof of no cloning theorem in this way. So let us suppose, if possible, there exists a cloning machine that can clone the arbitrary quantum state in this way. So what does this mean? What does equation 8 means? Equation 8 means that Ket S, this is the arbitrary quantum state. So Ket S is nothing but it gives you arbitrary quantum state A Ket0 plus B Ket1. This is the blank copy. So this is the blank. This represents a blank state. So that means whenever you are copying something, you have to give some blank paper on which the original has to be copied. Okay. So in the same way, we can put here some blank state on which we would like to copy this quantum information. Now this is the state Qi. This state Qi, it gives you the machine, that is the cloning machine, and Qi means the initial state of the quantum cloning machine. Because we know that whenever we were doing something, whenever we are performing some measurement on this some quantum state, so machine will change. So here also the machine also acts like a quantum state. So whenever after cloning operation, the state vector of the machine will change and it will become QF. This is the final version of the quantum state of the machine state vector. So now we want that this original has to be copied into this blank state. So that means this Ket is Ket sigma Kt Qi transform to Kt. So the original is copied into this one, the blank onto the blank state. So Kt Qf. So Qf is the final version of the quantum state vector, quantum machine state vector. So we would like to have this type of transformation, but unfortunately we will see that this type of transformation will not exist. Perfect cloning cannot be done with the quantum state. Okay, so we will prove it now. So let us take this arbitrary pure quantum state S is given in this way, alpha 0 plus beta 1. So let us consider this is our quantum state, and this state we would like to copy it. So here mod alpha square plus mod beta square equals to 1. So now whenever whenever we have this classical bit, so just put it here in place of qubit. We can just replace S by 0. So whenever we replace this state 0, so this is a classical bit, it has no superposition. So that means we have some machine QI, and that gives you the perfect copy, this one 0, 0, QA. So whenever we have this classical state vector, then that classical state vector can be copied perfectly. So this transformation gives you tell you the exactly the same thing as I have mentioned you. So this one K0, K sigma Qy gives you K0, K0, Q0. This is the final machine state vector, and 1 sigma Qy gives you 1, 1, Q1. So this is the final state vector when we are copying this K1 vector. So then when we have this thing, so in the left hand side S sigma Qi, so the left hand side will become the right hand side alpha 0, 0 Q naught plus beta 1, 1 Q naught. So you can see that we can just apply this operation 0 sigma Qi 0, 0 Q0 and 1 sigma Qi goes to 1, 1 Q1. So when we apply this thing, then we can have this this transformation. So this means that S is alpha K0 plus beta K1, alpha K0 plus beta K1, and you are applying this sigma. This is the blank copy and Qi. So now, since quantum mechanics is linear, so we can apply the linear property. So we have this alpha 0. This is the blank, then Qi plus beta 1 sigma Q1. So this alpha 0 sigma Q1 Qi according to this is so 0 sigma Qi, this goes towards 0, 0 Q0. So that means this goes towards this one alpha 0, 0 Q0, and then beta 1 sigma Qi. So 1 sigma Qi transformed as 1, 1 Q1. So that means this will become beta 1, 1 Q1. Okay, so in this way, the S sigma Qi goes towards this this state, that is alpha 0, 0 Q0 plus beta Q1, beta 1, 1 Q1. Okay, so now the right hand side, this is the this thing is the left hand side. This gives you the left hand side. Now let us calculate the right hand side now, because we would like to have this type of transformation. K S sigma Qi. We have already calculated this one. So now it remains to calculate this portion, this side, that is the right hand side. So right hand side tells us that if we have perfect cloning machine, we have we have this state in the right hand side. So that means K test QF. So let's calculate this one. So K test QF. So K test QF. So when you just expand it, then you will get alpha 0 plus beta 1, then alpha 0 plus beta 1. This is in between we have tensor, and then QF. So now if we just take the tensor product between these two, then you will get this thing alpha square 0, 0, alpha beta 0, 1, beta alpha 1, 0, and beta square 1, 1. So the right hand side will become this. So you can easily see that the left hand side and right hand side are not equal. They are not equal. That is why we cannot have this type of transformation. So quantum mechanics forbid this type of transformation. We cannot get any cloning machine that can clone any arbitrary quantum state. But one can do one thing. So you can just see here, if we put alpha equals to 0. So if we put alpha equals to 0, then this will vanish. And according to this condition, mod alpha square plus mod beta square equals to 1. So when you put alpha equals to 0, then beta will become 1. So when beta will become 1, then you can put here just beta equals to 1, then you will get this one. You will get this beta 1 1 q1. So you will get this state beta 1 1 q1. So in the right hand side, when alpha equals to 0, then this term will vanish, this term will vanish, this term will vanish, beta equals to 1, and we remain with 1 1 qf. So that means 1 1 state will when we have in the left hand side 1 state, so in the right hand side also we have 1 1. So that means whenever we are giving this transformation 1 sigma q1 1 1 q1, so this type of transformation will exist in case of classical machine. That means we can construct a classical cloning machine that can clone the classical bit. But in case of quantum state, we cannot have any quantum cloning machine that can clone an arbitrary quantum state. So this is the proof of no cloning system. So that means we cannot clone any arbitrary quantum state. So now, after this, let me introduce the concept of quantum entanglement. Because we need this quantum entanglement to describe this quantum teleportation protocol. So we know that it is a very fascinating feature of quantum mechanics, and it has no classical analog. And also, this entanglement plays a vital role in some quantum information processing, quantum information protocols. So likewise, teleportation, quantum superdense coding, all are in all these protocols we need entanglement. So you can have a different task here: quantum computing, quantum teleportation, quantum cryptography. All these tasks can be done just by using this quantum entanglement. So now let me give you the basic definition of quantum entanglement. So let us consider two subsystems A and B, which is described by the Hilbert spaces HA and HB respectively. Okay, so that means we can have these two subsystems, one subsystem lying here, and it is described by this Hilbert space HA, and the another subsystem B, which is described by this Hilbert space HB. So now, if we would like to combine these two systems, then that combined system is denoted by the composite system, and this composite system is described by the tensor product between these two Hilbert spaces, HA tensor HB. Now, if we have any state, so here you can see that this is psi AB, so this is a vector. So vector implies that this is a pure state. So when we are considering this pure state, so pure state is represented by the vector quantity, and mixed state is always represented by the density matrix. So always you can find out the density matrix of the pure state also, or you can write in this way. So this gives you the density matrix corresponding to this state psi AB. It is a pure state, but one thing is that here you can get this condition rho square equals to rho. But in case of mixed state, you cannot get this condition rho square equals to rho, and you will get rho square is less than rho. So in case of mixed state, rho square is less than rho, and in case of pure state, you should have rho square equals to rho. This is the checking point that whether the state you are considering is a pure state or the mixed state. So here also one more thing is that the trace of, if you take trace both sides, then you will get trace rho square is less than trace rho. So trace rho equals to 1, because trace rho gives you the sum of the diagonal element of this density matrix, and sum of the diagonal elements gives you the probability. So the total probability must be equal to 1. So that is why trace rho equals to 1. So trace rho square less than 1 means if you verify that whatever rho you are considering, and for that row, if you are calculating this trace row square and it comes out to be less than 1, then you can assure yourself that the state you are considering is a mixed state. If trace row square equals to 1, so this gives you this pure state. So trace row square gives you the trace row square equals to 1 gives you the pure state. So here you can see that psi AB, which also you can discriminate pure state and mixed state in this way, that pure state always gives you a vector quantity, but is a vector, just a vector, but rho, this, if you have density matrix, then it is given by some outer product of this convex combination of this pure state, that is vectors, convex combination of this type of vectors, then you will get a mixed state. So a pure state psi AB belongs to HA tensor HB. Let us suppose if we have this Hilbert space HA tensor HB, this is the composite system, HA tensor HB. And let us suppose if you compose these two subsystems, then you will get a total system of this comprising these two subsystems, and that subsystem can be denoted by psi AB. So psi AB is belongs to HA tensor AB. So this state is called a separable state. So that means separable means one system is not linked with the second system. So that means if the system A is not linked anyway to this other system B, then we can say that these two systems are separable system. So and mathematically we can write that any state psi1 which is lying in this subsystem and any state psi2 which is lying in this subsystem, if psi AB can be written as psi1 tensor psi2, where psi1 belongs to this Hilbert space HA and psi2 belongs to this Hilbert HB. If psi AB is can be written in this way, then you can conclude that the state you are considering, the pure state you are considering, is a separable state. So you can see that that means this separability means that if you are performing any measurement on this system, it does not affect the second system. In the same way, if you perform any measurement on the second system, it does not give any effect on the first system. So that means these two systems are independent with each other. Okay, so then we can say that if this type of thing will happen, then you can say that the state psi AB represents a separable state. And if the state is not looking like this, so those type of states are said to be an entangled state. This means that if you perform some measurement on this, and if you feel some effect on this system, then you can say that the state is entangled. Okay, and if you don't have any effect of measurement on the system A, and system B is not realizing that measurement effect, so we can say that that system is a separable state. So now this is the definition for the pure separable state. So now in case of mixed state, if we write the convex combination of this type of separable state, so that means if we write the convex combination of the tensor product of two individual system, then we can say that the state is separable. Otherwise, if we cannot write in this way, then we can say that the state is entangled. So this is the basic definition of the entangled state mixed system, and in the above, this is the definition of the separable system in case of pure state. Now here we can have a example of a pure separable state. So a general 2-qubit pure state can be expressed in terms of the computational basis. So this is the computational basis. So in a two-dimensional Hilbert space, so HA is the two-dimensional Hilbert space. So it is 0, and all elements of HA span by these two basis elements 0 and 1. In the same way, HB, this is the Hilbert space B, this is also spanned by these two basis elements 0 and 1. So when you take the composite system, so that means you are taking the tensor product of these two. So that means you are getting HA tensor HB. HA tensor HB. So in this system, we have the basis element 0, 0, 0, 1, 1, 0, 1, 1. So that means these 2 cross 2 system, if you take the these two qubit system, this is the qubit system, this is the qubit system. If you take the 2 qubit system, so that 2 qubit system is expanded or spanned by this computational basis K00011011. So that means any general state in HA tensor HB, where HA and HB are 2-dimensional Hilbert spaces. So any general state in this HA tensor HB can be written in this way: alpha 00 plus beta 01 plus gamma 10 plus delta 11. So it is the convex. It is the linear combination of this. That means it represents the superposition of this basis state. And with the normalization condition, there is mod alpha square plus mod beta square plus mod gamma square plus mod delta square equals to 1. This gives you the normalization condition. Now, if we choose alpha equals to beta equals to 0, so that means mod gamma square plus mod delta square equals to 1. So here, if you put alpha equals to 0, beta equals to 0, so you can see here that this state reduces to gamma 10 plus delta 11. So now you can see that from this, you can easily separate the system A. So you can write this system, this system can be easily written in this way. So 1A, so that means you can take out 1A, that is system system A you can take out, and the other system B can be written in this form: gamma 0B plus delta 1B, where mod gamma square plus mod delta square equals to 1. So you can see that whenever alpha equals to 0, beta equals to 0, so then this total system, this total 2 qubit system can be written in this way. And you know that whenever we can write any pure state in this form, then it is a separable, it represents a separable state, because if you perform some measurement on it, then this second system doesn't feel any effect of that measurement. Again, if we choose alpha equals to half, beta equals to half, gamma equals to half, delta equals to half. So that means if here we have chosen all non-zero parameters, so then you can, again, if you put here alpha equals to half, beta equals to half, gamma equals to half, delta equals to half, then you can easily factorize this thing, and you can write the total system, AB system can be written in this way: 0A plus 1A tensor 0B plus 1B. So again, you can see that the two systems can be easily separated, and one system is not linked with the second system. So that means, according to the definition of the separability of the pure state, we can say that this state also represents a separable state. Now, if we choose again alpha equals to delta equals to 1 by root 2, and beta and gamma equals to 0, then the state can be written in this way. So you can see here alpha equals to delta equals to 1 by root 2, and beta equals to gamma equals to 0. So if beta equals to gamma equals to 0, that means this two state will go out, and we remain with only this two, one alpha 00 plus delta 11. And if you put alpha equals to 1 by 2 and delta equals to 1 by root 2 and delta equals to 1 by root 2, then the normalization condition also holds. So whenever we have this type of thing, so we remain with this thing 1 by root 2 00 plus 1 1. So in this case, you can easily see one system is not linked with the others, is linked with the other system. So if you perform some measurement on one system, any one of the system, then the second system realize that effect. So that means this system is the example of a entangled system. In the same way, we can have this state also 1 by root 2 0 1 plus 1 0, which is considered as an entangled state. This is another example of an entangled state. Now, here you can see the just in this slide, we can have a measure of entanglement. That means if the state is entangled, it is necessary to know how much this state is entangled. So what would be the value of the entanglement? So this value of the entanglement gives you the feeling that whether we have two states. So let us consider two states, psi1 and psi2, and both are entangled states. So now if we would like to quantify the amount of entanglement, whether the entanglement in psi1 is greater than entanglement in psi2, or can we have any state psi3 which is whose entanglement is greater than both psi1 and psi2? So to measure, to compare this thing, to measure to compare the amount of entanglement, we need to introduce some measure of entanglement. And in this case, we can introduce a measure of entanglement as a concurrence. So for 2 cross 2 system, this is a common measure of entanglement. So let us see that for pure state, any pure state alpha 00 plus beta 11 we can consider, gamma delta we can put 0. So that means alpha 00 plus beta 11 mod alpha square plus mod beta square equals to 1 is the normalization condition. So when we calculate the concurrence of this, so concurrence of this state can be calculated just by taking the inner product of psi tilde psi and taking the modular sign. So what is psi tilde? Psi tilde is nothing but sigma y tensor sigma y psi. So this psi tilde is defined in this way. So it is very important that this Pauli matrix sigma y, this Pauli matrix plays an important role in the entanglement theory of entanglement, in comparison to sigma x and sigma z. So if you go through the Utter's paper, so I forgot to give you the reference here. So there is a paper by Utters in which you can just get the flavor of this derivation of this concurrence C psi AB, and that derivation he has done for the mixed state also. So if you calculate this state psi AB, the concurrence of psi AB for where psi AB is represented in this way, alpha 00 plus beta 11, and if you calculate this thing, then you will get 2 mod alpha mod beta. So now one thing we would like to see that, what would be the amount of entanglement content in it, and what would be the amount of entanglement content in it. So when we have this thing, so you can put alpha equals to 1 by root 2, beta equals to 1 by root 2. So if we have alpha equals to 1 by root 2, beta equals to 1 by root 2, so then you can easily find out 1 by root 2 and 1 by root 2. So you can see that 2 cancel, 2 will cancel, and you will get 1. So concurrence of psi will be equal to 1, and it is the highest value of the concurrence because the concurrence lying between 0 and 1. Concurrence will be equal to 0 when it is a separable state. So you can easily see that whenever alpha equals to 0 and beta equals to 1, so that means this state psi reduces to 1, 1. So this means that 1, 1, this 1, 1 is nothing but it can be represented like this, 1 tensor 1. So this represents a first system, this represents a second system. And you can see here, just by this formula of the concurrence, if you put alpha equals to 0, so we will get here alpha equals to 0, beta equals to 1. So when you put here alpha equals to 0, beta equals to 1, then you will get that the value of the concurrence will be equal to 0. So value of the concurrence will be equal to 0 implies that the state which we are considering is a separable state, and it is clear from this definition also. So in this way, we can calculate the amount of entanglement just by using the concurrence of the given state, and this is the formula for the concurrence of the mixed state. So I'm not going into the detail of it. So now, okay. So now, before I will proceed towards the classical teleportation, so I would like to show you a video first, and then I will proceed. So you can see that in early 80s, in early 1980s, when I was kid, so I was watching the TV serial, that TV serial named as Star Trek. Okay, so in that Star Trek, I have seen first time the concept of teleportation. Okay, so at that time it was just fictitious thing, and we can just imagine the concept of teleportation at that time, and now we can realize this thing experimentally. So just I would like to show you this video of a Star Trek where this concept of teleportation has been introduced. So now let's come back to our slide. So you can see in that Star Trek movie, you can see that some persons vanishing from vanish from one place and reappear in some other place. So you can observe that the person which is vanishing, who is vanishing from one place, so he is vanishing from one place, but and reappearing to some other place, but it's his copy is not there. So that means he is not present in the two places simultaneously. So that means in one place he has to disappear to reappear to some other place. Okay, so this is the no cloning theorem. So in the Star Trek movie, they have teleported a person, a man, a human being. They have introduced the concept of teleportation in case of human being, but it is not possible till now. Okay, so we can teleport just a state of a quantum system. So if we have some state of a quantum system, that state can be teleported, but we cannot teleport a human being right now. Okay. So this is the concept of teleportation. So I will introduce in a more simpler way. So let me first talk about this classical teleportation. So how classical teleportation deals with this type of fact, this type of protocol. So in the classical so here we are talking about classical teleportation of a qubit. So that means the system which we are going to teleport, that is a qubit. Okay, so it is a quantum bit, and we are going to teleport this quantum bit by some classical means. So we will not use here any quantum resource to teleport a quantum bit. So if can we do this? So Masser and Popescu showed that yes, we can do this. We can teleport some quantum bit. Okay, but with some restriction. So what they have done, they have considered n copies. So n copies of a system, and then they have performed a measurement on these n copies, not on this single copy, but they have performed measurement collectively on n copies, and then try to achieve information and try to extract information from that n ensembles. So whenever they have applied this optimal measurement strategy, so optimal measurement strategy gives us the amount of information we can extract from this n ensemble is n plus 1 by n plus 2. So that means if we have n number of systems, then we can measure on this collectively on this n system, and then after measurement we can extract some information from there, and that information can be obtained, whose value is given by some fidelity, and that fidelity comes out to be n plus 1 by n plus 2, and it is the optimal fidelity, means optimal information we can extract only this thing. If n, so that means we have n number of system, we can measure collectively on n number of systems, and then we can extract information from there, and that information can be computed just by using the concept of fidelity. So that means the fidelity means overlapping between the input state and the output state. So that means before we perform measurement, so we have some state representing this n state, n ensemble, and then after performing measurement, psi will change, and then it will become psi tilde. So at the output we have psi tilde. So now we can just take the overlap between psi and psi tilde. This gives you the fidelity. Okay, so the amount of fidelity, the value of the fidelity comes out to be n plus 1 by n plus 2 when we have n number of ensembles in our position. Okay, so now this is called prepare and measure strategy. So this strategy is called prepare and measure strategy. So now if we have a single qubit now, So now we are considering here n equals to 1. So if we have only single qubit, not copies of single qubit, because we cannot copy it. Okay, perfectly we cannot copy it according to no cloning theorem. So whatever we have to do, we have to do on this using this single copy of a qubit. So whenever we have this single copy of a qubit, then what we can do, we can just prepare that copy of a qubit and perform measurement on that, extract information from there, and then you can repeat this process again and again. So when you are repeating this process again and again, then you can get the total fidelity that comes out to be 2 by 3. This is the total fidelity of fidelity, that is the overlapping between the input state and output state, comes out to be 2 by 3. You cannot go beyond this value. If you adopt this prepare and measure strategy, that means prepare the single qubit of a qubit and then perform measurement on this and extract information from there. If you do this process again and again and again and again, then you can get the fidelity is 2 by 3. You cannot go beyond this 2 by 3 fidelity. So that means when you are doing this prepare and measure strategy, we are applying the classical apparatus there. We are applying all the classical resources. We are not applying any quantum resource there. Only the quantum thing is there, that is the qubit. Only the qubit means from which we can extract the information. The information contained in a qubit is infinite. Okay, so that means in a real lifetime, we have to perform finite number of, we can repeat the experiment a finite number of times. So to do, by doing this, we can get the, we can extract the information only by this amount, 2 by 3, not beyond that. Okay, so this type of strategy is given in this paper. So if you would like to see this value, how 2 by 3 has 2 by 3 comes, so you can just follow this paper. You can just go through this paper, and then you can have this this result, that whenever we apply the optimal strategy, whenever we are optimal measurement apparatus on a single copy of a qubit to extract information from the qubit, then we can extract information only up to the 2 by 3 in terms of fidelity. Only the fidelity is 2 by 3 and not beyond that. So this is known as classical fidelity, because we are applying only classical resources to extract from the quantum state, to extract information from the quantum state. So this classical fidelity is 2 by 3. The maximum value will be equal to 2 by 3, and if you are not performing optimal measurement, then the classical fidelity is less than 2 by 3. So this is the classical case. So now the question is that if we have a single copy of a quantum system, so if we have a single copy of a quantum system, so can we have some quantum resource so that we can extract information more than 2 by 3? So this is the question. So you were given a single copy of a qubit, and we would like to extract information from there, and can we have some and we also know that the classical resource cannot give you the fidelity greater than 2 by 3. So the question is that whether we can use some quantum resource so that we can have the fidelity, we can make the fidelity greater than 2 by 3. This is the question. So this question was answered by Bennett and all others in their seminal paper, and they have introduced the concept of quantum teleportation, and they have shown that there exists a quantum resource. If we use that quantum resource, then we can just extract the information greater than 2 by 3. So what would be the objective of the quantum teleportation? So the objective of this quantum teleportation is to transmit the structure of the objects between two distant partners, Alice and Bob, by sending two classical bits. So here we would like to extract information. So that means if Alice Alice can perform measurement on it. Alice can perform a measurement on a qubit. Let us suppose Alice has some information encoded in a qubit, and she would like to transmit this information to Bob. So then she can take two paths. First path is that she can use classical resources and then perform measurement on it and extract information, and this thing she will repeat again and again, and then she has information information 2 by 3. That means 66.6% information she can extract from this qubit, and then she can just over the telephone she can tell to Bob that this type of information I have collected, so you can use this information to make a copy of it. Okay, so in this way Bob just take this information, and then see he can make a copy of it, and then he can just but he can make a copy about 66.6% copy he can make, but not 100% or not beyond 66%. Okay, so but now our task is to use the quantum resource. So can we have any quantum resource by which we can this Alice can send the information to Bob beyond 66.6%. So that means can Alice send the information contained in a qubit to Bob with 100% efficiency? So this is the question. So this is the objective. This is the objective of this quantum teleportation protocol, and the objective is here clearly written that that Alice has to transmit the structure of the objects between transmit the structure of the object by sending two classical bits. So here you can see that whenever Alice would like to transmit some information encoded in a qubit, so qubit will go to the to Bob's side just by using quantum resource, but Bob cannot access that information until Alice spend the two classical bit, or Alice send some information just by using two classical bits. Okay, so so that means classical and quantum both will be required to for the success of the quantum teleportation protocol. So I will show this protocol just in a pictorial way. So let me show you this picture here. So you can see that this is Alice, and this is the she is the sender. That means she would like to send some information encoded in a qubit to his distant partner Bob. So Alice is working in this lab, which is described by this Hilbert space HA. Okay, now here we have Bob, and Bob is working in this lab, which is described by this Hilbert space HB. And their labs are far apart from each other. So now Alice would like to send this state alpha 0 plus beta 1, this qubit, to Bob. Okay, so if Alice uses a classical resource, then she can transmit the information contained only 66% to Bob. Only 66.6% information contained Alice can send to Bob if Alice use only classical resource. Okay, but we can use the quantum resource also, so that we can send the qubit or send the total 100% information to Bob. So for this we need this entangled state. So now you can see that this entangled state is 1 by root 2 0 0 plus 1 1, and we have already seen that this is a maximally entangled state. So that means the amount of entanglement in this state is 1. The value of the concurrence is equal to 1. So this is the maximum entanglement contained in it. So that is why it is called maximally entangled state. So to teleport or to send the information contained in this state just by using via this entangled state, this maximally entangled state. So now what is the protocol, how protocol works? So first of all, what we will do, we just take the tensor product of these two states, psi1 tensor b23. So if you take the tensor product, so then you will get alpha 01 plus beta 11, beta 1, Kate 00 plus Kate 11 by root 2. So just take the tensor product after simplifying, and then you can write in this form. So we have written here 1, 2 in one place, and 3 is another place, because these 1 and 2 qubit are with Alice's position, and 3 is with Bob position. So that is why we have just written in this way. After this, Alice performed some C0 gate operation. So C0 gate is an unitary operation, and this operation is performed by Alice on her 2 qubit that is with her. So Alice is with 2 qubit, 1 qubit, qubit number 1 and qubit number 2. So on this 2 qubit, Alice performed this C0 gate operation. So C0 gate, the operation of C0 gate is in this way. That means it can be described in this way. The transformation is described in this way. C0 gate transformation is described in this way. That is 0, 0 goes to 0. That means if we have the first qubit 0, then at the output nothing has happened. So 0, 0 gives you 0, 0, 0, 1 gives you 0, 1. But whenever the first qubit is 1, the second qubit will flip. This is the beauty of this transformation. So 1, 0 gives you 1, 1, and 1, 1 gives you 1, 0. So this is the C0 gate operation. So when Alice applying this C0 gate operation on her 2 qubit, the resulting state will now this one. So the state will now reduces to this one. So you can see that 0, 0 is there. So it will be 0, 0, because 0, 0 goes towards 0, 0. And then 0, 1, it remains the same, 0, 1. Now 1, 0. 1, 0 will become 1, 1. And 1, 1 here will become 1, 0. So just by writing this state in this way, 0 alpha 0 1 tensor 0 2 3 alpha 0 1 1 1 2 3. So just rewrite this above state in this way, and then Alice again apply this Hadamard gate transformation on his qubit, on her qubit. So this 0 1 on this 0 1 qubit, that means 1 means the qubit 1, qubit number 1. So Alice performed this Hadamard gate operation on her qubit number 1, and after this operation, she remain with this state. 0 0 state will appear after performing this Hadamard gate operation. So now you can see here that the first 2 qubit can be written in this way. Collectively, you can just, if you collect first 2 qubit, then you can just write or rewrite this state in this way after performing this operation. So you can now see that this state, which is now which is initially possessed by the Alice, that is alpha 0 plus beta 1. So it is with qubit number 1. So now in this state, you can see that this type of state is now with 3, and the qubit number 3 is with Bob. So that means this alpha and beta transferred to Bob's qubit. Okay, so this information contained in only alphas and betas. So the information contained in alphas and betas means that the information is already shared with Bob, but Bob don't know whichever state he has received, which state he has received. This state he has received, or this state he has received, or this state, or this state. He doesn't know about this. So that is why the information is transmitted from one place to another place, but Bob cannot retrieve that information until Alice informed that which measurements he has performed. Okay, so now after this, after getting this type of thing, one thing here remain, that Alice has to perform measurement on 00011011 basis. This is known as this 2-qubit computational basis. So whenever Alice measure 2-dimensional computational basis, that is 00011011, so then the state goes either in this form, either in this one, or this one, or this one, or this one. So this 4 will represent this thing: alpha 0 plus beta 1, alpha 1 plus beta 0, alpha 0 minus beta 1, and alpha 1 minus beta 0. This 4 state is represented by this one. So Bob received this state, but he don't know what state, which state he has received from Alice. So to do this, to get the information that which state he has received, Alice has to perform measurement in this computational basis. And after measurement, Alice just make a call to Bob to let him know that which measurement outcomes he has got. Okay, so if the measurement outcome is 00, then state is received by Bob. Okay, but if the measurement basis is 01, if the measurement outcome is 01, if Alice got this measurement outcome, then Bob received this state alpha 1 plus beta 0. So the information of the measurement outcome Alice sent to Bob just by using 2 classical bits. So if Alice sends 00 to 2 classical bit, that means 00 she can send either 01 or 10 or 11. So if Alice sends 00 to Bob, this means that Bob received this state alpha 0 plus beta 1. If Alice sends 01, then Bob received this state alpha 1 plus beta 0. But this is not the original one which Alice would like to send. So after getting the measurement outcome from Alice, Bob just perform a unitary operation on this. And you can see that if Bob performs sigma x operation on the received state, then the received state will now reduces to the state which Alice wanted to send. So that means if sigma x operated on this, so that means sigma x1 will become 0, that means flipping operator, and sigma x0 will become 1. So alpha 0 plus beta 1, Bob will receive. So in this way, the teleportation protocol works. And one more thing you can, here, I should let you know that whenever this state goes from Alice to Bob's side, Alice lost his state, and the entangled state that is required to send that state, that qubit, that also lost. So that means the shared entangled state lost, and the state which Alice wanted to send, that also vanishes from Alice's side. So that means there does not exist any copy of it, copy of that unknown quantum state that Alice wanted to send to Bob. So this is because of the no cloning theorem. So now the point is that here in this teleportation protocol, you may observe that this quantum resource, that is the shared entangled state, play a vital role in this teleportation protocol. So now I will talk about this role of this shared entangled state. Okay. So now, I will already show. I have already shown you that this pure maximally. If the two partners, Alice and Bob, shared maximally entangled state, then the unknown qubit can be teleported from one place to another place with 100% fidelity. But in a real situation, we won't have this pure maximally entangled state, because whenever you would like to set up this resource state, you have to generate the entangled state from some common source. Okay, so when the common source or when the source generates some entangled state, after generating this state, this source send the two particle, that means one particle to Alice and one particle to Bob. So whenever this source is sending the qubit, one qubit to Alice, one qubit to Bob, so this qubit is traveling through the environment towards Alice, and also traveling through the environment towards Bob. So when the qubit is traveling through the environment, it interacts with the environment, and because of this interaction, the state is lost. So at the initial stage, means in the source generate the maximally entangled state. Okay, but when source is sending the qubit to two different places, so the maximally entanglement will become lost. So this state either will become separable, or if it is not separable, then maybe we can. It is the worst case, the separability case. But if it is not separable, so the amount of entanglement will diminish. So that means if the amount of entanglement will diminish, so that means the state will not remain as a maximally entangled state. So if the state will not remain as a maximally entangled state, then Alice and Bob has to use this non-maximally entangled state as a resource state to execute this teleportation protocol. Okay, so to execute this teleportation protocol, either Alice and Bob has to use this non-maximally entangled state or some mixed state. Okay, but in both of these cases, we cannot have the fidelity equal to 1. We cannot have the fidelity equal to 1. But in case of non-maximally entangled state, we can make the fidelity equal to 1. But we have to go through the probabilistic protocol. We have to go through our protocol will not remain the deterministic protocol. That means with probability 1. So this means that our protocol will not work every time. So there exists some probability for which the protocol will work if we use pure non-maximally entangled state or mixed state. Okay, so I will show you here that if we use pure non-maximally entangled state, then the quantum teleportation protocol will work probabilistically. So here you can see that if instead of maximally entangled state, we can use this non-maximally entangled state. So you can see that if you put n equals to 1, then this state reduces to the maximally entangled state, because it will become 1 by root 2, 0, 0 plus 1, 1. And you know that this is a maximally entangled state. But if n is not equals to 1, so it will be a pure non-maximally entangled state. So when you would like to teleport some qubit, this qubit is given in this form alpha 0 plus beta 1 using this pi AB as a resource state, then you cannot achieve the faithful teleportation. So that means you cannot teleport this state psi 1 faithfully. So that means you can send the state with unit fidelity, but not with unit probability. Okay, so there exists some non-zero probability for which this protocol will work. It will not work always. So this sacrifice we have to make here. Otherwise our protocol will not work with the pure non-maximally entangled state. So this work, if you would like to go through this work, then you can consult this paper in 2002. It's published in Physics Letters A. Now, after discussing this non-maximally pure state, which is probabilistic protocol, but we would not this approach, this probabilistic approach is not suitable for us. So we can use the mixed state as a teleportation protocol, and we would like to make our protocol success every time. So we would like to make our protocol success every time, and so to do this we can use the mixed state, because in real life we have only the mixed state in our possession. So we assume that Alice and Bob shared a mixed entangled state. Okay, so there are different types of mixed entangled state. So we can talk about here maximally entangled mixed state. So this state, maximally mixed state, means this we have, let us suppose this, we have row 1, row 2, row n. This is the set of state, and the linear entropy measures the mixedness of this state. And if we use this one, SL row 1 equals to SL row 2 equals to SL row n. So if the mixedness of these states are all equal, and then if we find that among this state with the same mixedness, the maximum amount of entanglement contained in it, then we can say that these states is a maximally entangled mixed state. So maximally entangled mixed state means the set of all mixed state with some fixed mixedness. So that means mixedness is given to you. So mixedness is same for all these mixed state. We are considering all those states, and then we can just calculate the concurrence of this. So if we have concurrence of C row 1, which gives the amount of entanglement in row 1 greater equal to C row 2 greater equal to C row 3, like this. If we have this thing, then you can see that the concurrence of this row 1 is greater than all this. So that means in this set, row 1 is the maximally mixed state. So in this way, the maximally mixed state is defined. And this term is introduced by Ishizaka and Hiroshima in this paper. So they proposed a class of bipartite mixed state and showed that entanglement of those states cannot be increased further by any global unitary operations. So if you perform any unitary operation, global unitary operation means not local. So we have 2 qubit system. So we have 2 individual systems, and globally we have to act this unitary operation on this row 1. So if this unitary operation will act globally on this row 1. So and then if we see that the entanglement is not increasing, then we are saying, we can say that this is a maximally mixed state, because this has the maximum entanglement in it, and no further entanglement can be introduced in it. So Ishizaka and Hiroshima introduced this class of bipartite mixed state where the entanglement cannot be increased just by using global operation. Later, Munro also gave a class of state with maximum amount of entanglement for a given degree of purity or degree of mixedness. So, sir, how much time I have?
Yeah, you can take it, no problem.
Okay. So now, so MJKW is a class of state which is provided by Munro, James, White, and Quiet. So this state is the maximally entangled mixed state. So this is the analytical form of the maximally entangled mixed state, and this mixed state. Here you can see this mixed state is in this form, and here C denotes the concurrence. C denotes the concurrence of this state. So C denotes the concurrence of this row MEMS, and HC, this is the function of the concurrence, and it is equals to C by 2 when C is greater equal to 2 by 3, and it is equal to 1 by 3 when C is less than 2 by 3. And you can just calculate the linear entropy of this maximally entangled mixed state, and after calculation of this linear entropy, you will get this expression. and the optimal fidelity. So now the important point is that if you use this maximally entangled mixed state as your resource state to teleport a qubit, then the optimal teleportation fidelity comes out to be 2c plus 1 by 3. So that means here you can see you can observe one important point, that the optimal teleportation fidelity is a function of the concurrence. So as the amount of entanglement increases, the optimal value of the teleportation fidelity will increase. So if you can see here, if the maximum value of C is greater or equal to 2 by 3 but less than or equal to 1, so you can see that if C equals to 1, so it will be 2 plus 1, 3, 3 by 3, 1. So teleportation fidelity will be equal to 1. Okay, but one thing we must be careful about this, that this is a maximally entangled mixed state. So this is a mixed state. So concurrence of any mixed state cannot be equal to 1. So the concurrence of any state will be equal to 1 if it is only a pure state and if it is of this Bell state form. So that means either it of the form alpha 1 by root 2 0 0 plus 1 1, or 1 by root 2 0 0 minus 1 1, or 1 by root 2 0 1 plus 1 0, or 1 by root 2 0 1 minus 1 0. So these are the 4 states which gives you the maximum amount of entanglement, and they are known as Bell state, and they are known as maximally entangled state. But if you have mixed state, then their concurrence certainly not equal to 1, and hence this teleportation fidelity should be less than 1, but cannot achieve the value 1. So here you can see that you can observe, if you go through that paper, you can observe that the maximally entangled mixed state can be used as a faithful teleportation channel when the mixedness of the state is less than the value this. Okay, so 22 by 27. So you can see that mixedness is very, very small and close to 0. So close to 0 means if the mixedness is 0, that means it goes towards the pure state. So if you so we found that if the mixedness is 22 by 27, so then the faithful teleportation means the fidelity is greater or equal to 2 by 3, greater than 2 by 3. So now the question is that if we take, so from this, can we conclude that if we take maximally entangled mixed state as our resource state, then we can have the faithful teleportation. We can do faithful teleportation. So the answer is no. All maximally entangled mixed state, using all maximally entangled mixed state, you cannot achieve the faithful teleportation. Okay, so we found that Warner state is there. There exists a special type of 2-qubit mixed state that is known as Warner state, and it always acts as a better teleportation channel for all finite values of mixedness, even though they are less entangled compared to MJWK state for a given entropy. So that means Warner state is such a type of states. If the mixedness, if we consider this state Warner state, and just consider this state MJWK state and Warner state, and just calculate the entropy of these two states, and whatever value you will get, just fix it. So that means make the entropy equal for these two states. So if you make the entropy equal to this state, then that means that the mixedness is same for these two states. But you can find that this Warner state serve better as a teleportation channel than this mixed state. Okay, and then later you will see that this Warner state is also not a maximally entangled, not comes under the category of maximally entangled mixed state. So this is a non-maximally entangled mixed state. So this is a non-maximally entangled mixed state, but it serves as a better teleportation channel than all other maximally entangled mixed state. So this question, the answer of this question is obviously no. So we cannot always have maximally entangled mixed state as our teleportation channel. We cannot do the teleportation, good teleportation or faithful teleportation using just maximally entangled mixed state, because we have Warner state through which we can do better teleportation.
Can you finish within 5 minutes, sir?
Okay.
Ah.
Okay, within 5 minutes I will complete it.
Yeah.
So I will just skip this thing and then so I would like to give you the flavor of super dense coding. So within 5 minutes, I will complete it. So super dense coding, what do you mean by super dense coding? The goal of super dense coding is to transmit some classical information from Alice to Bob. So here we are transmitting classical information from Alice to Bob. So if Alice wishes to send 2 classical bits to her distant partner Bob, then how she will achieve her goal? So let us suppose that Alice and Bob shared a maximally entangled state. So what is this goal? What is this concept here? So I just give you in this pictorial form. So here Alice and Bob shared a maximally entangled state. Let us suppose Alice and Bob shared a maximally entangled state. Which is of this form? Which is of this form? Okay. So now here this qubit, first qubit is with Alice and the second qubit is with Bob. Okay, so then what how Alice transmit these 2 bits of classical information to Bob to do this job complete to complete this job Alice performs some local unitary operation, that is I, sigma x, sigma y and sigma z. So Alice perform operation, unitary operation on her qubit. So if she performs I on her qubit, so that means this state will remain same. So if she performs sigma x on her qubit, so that means when sigma x perform on this, so that means globally sigma x tensor I is the operation. I means Bob is doing nothing and Alice is performing sigma x operation on her qubit. So when sigma x is operating on first qubit, so sigma x when operating on this changes to 1, 0 changes to 1 and 1 flipping to 0. So that means this state now reduces to 1, 0 plus 0, 1. So in this way, Alice perform the other 2 measurement, other 2 unitary operation also, sigma y and sigma z. So if she perform this type of operation on this state, so this state reduces to this one. The shared state reduces to this one. When I operate, when Alice is operating I, so the state will remain same. When Alice is operating sigma x, this state will remain will goes toward this one 1, 0 plus 0, 1. When Alice is operating sigma y, so the state will reduces to this one, and sigma z applying sigma z, the Alice this reduces to this one. So after performing this measurement, Alice send her qubit to Bob physically. Thus send this qubit to Bob. So that means first Alice and Bob share this maximally entangled state, which is of this form 0, 0 plus 1, 1 by root 2. So now after that, Alice perform I, sigma x, sigma y and sigma z on her qubit, and due to this unitary operation, the shared state is reduces to this 4 form, either this or this or this or this. And after that, Alice send this her qubit to Bob. So that means this qubit is sending to Bob. So now Alice has nothing with her, but Bob is with 2 qubit with him. Okay, so now this is an entangled state, and Bob poses this entangled state, and then Bob performs Bell state measurement on this on these 2 qubit. So when perform Bell state measurement means this one is the 5 plus 5 this 5 minus, this one should be 5. This one is the psi plus, this psi minus, and this is 5 minus. So you can see that all these states are orthogonal to each other and they are linearly dependent. So that means they forms a basis. So Bob performs measurement in this Bell basis. So after performing measurement, Bob will get either this one or this one or this one or this one. So whatever measurement outcome he will get, so he can he just means he just let's suppose if Bob gets this outcome 1 by root 2 0 0 plus 1 1. So it is clear, means it is pre-decided that if this state will, we are sharing this 5 plus, and if Bob is getting this state, so that means Alice is performing I operation. If this is already pre-decided, if it is 0 1 plus 1 0 plus 0 1, so then Bob Alice is applying sigma x. In this way, corresponding to this, we have sigma y, and corresponding to this state, we have sigma z. And since we have this 4 information to Alice would like to give this 4 information to Bob, so that this 4 information can be encoded and can be encoded through 2 classical bit. So minimum 2 classical bit is required to encode this information. So 0 0 0 1 1 0 and 1 1. So whenever Alice Bob get this information, this state, this measurement outcome, so so Bob will know that Alice has sent to you, sent him 0 0 classical bit. If Bob got this measurement outcome, so Bob will know that Alice sent this information 0 1. So in this way, 2 classical bit information can be sent through this super dense coding protocol. Thank you.
Okay, sir. Thank you very much for your this very excellent work on explanation of different aspects of teleportation and super dense coding. And a lot of work has been explained by you. And I think our participants has very much benefited from this lecture. So
Thank
any
you.
question? Any question from our participants? Any question, or you can write it in the chat box. Okay. I think they have no questions right now. So thank you, sir.
Thank you.
And,
Thank you, sir.
Thank you very much for your presence here in this FDP program. Now you can close your sharing. Stop sharing. You can stop sharing now.
Okay, okay.
Yes, Dr. Adhikari, you can stop sharing.
Sir, from where I didn't find that one. Stop sharing.
Yeah, that is on the upper side. You have whatever you have just showing. There is option of stop sharing.
Okay, okay, fine.
Yeah, fine. Okay. Okay. So thanks a lot for your presence here. And looking forward to see you again in future in GTU or anywhere. Okay, sir. Thank you.
Okay, okay. Thank you very much.
Okay. Now you can leave it. Leave the end
Okay,
meeting.
okay. Thank you, sir.
Yes, participants. This is the end of session 6 now. Tomorrow we have session 7 about quantum gates and circuits by Dr. S. Mishra, ITBHU. So please attend and in the morning tomorrow, and we meet at 9:30 a.m. Okay, thank you very much.